Okay, so welcome back, everybody. If you recall, what we were doing in our last class, we were trying to prove Picard's existence and uniqueness theorem. Okay, fine. So I'm just going to restate it briefly. So what it tells you, that suppose I have a given differential equation, of course first order, and this is nothing but an initial level problem. Okay, so this is your initial condition, and then it says that if both f and partial derivative of f with respect to y, they are continuous in some rectangular region, in R2, rectangular region R in R2, then there exists a unique solution in the neighborhood of x naught given by this inequality where h is greater than 0. Okay, so we have already found out how to choose h. Again, I'm going to come back to that again. Okay, so I will try to answer some pertinent question related to choosing that subrectangle R prime, which we used while trying to prove this theorem. Okay, now if you recall what we did, sorry. We were trying to prove this theorem in 3 steps. So step number one was that we were generating a sequence. Your yn. You know how to go about it. So again, anyway, I'm going to come back to this again. So we have to prove that this sequence converges to some function. Okay, and then number 2, this limit of this sequence, this is a continuous solution of equation number 2, which is nothing but the integral equation, right? And then number 3, it is a continuous solution, and number 3 we have to prove that this is the only continuous solution of 2 in R prime. Okay, fine. So if you recall, what we did, I mean, the choice of our R prime was something like this. Choice of our R prime was something like this. Say suppose this is x naught, this is x naught minus h, this is x naught plus h, this is y naught minus mh, this is y naught plus mh, this is y naught, of course this is the point x naught y naught, and this region, this shaded portion, we have defined it as R prime. Okay, anyway, I'm going to come back to that again. And please recall that in my last class, I mean, after watching my recording, I figured out that instead of this axis being x, I think in some of the figures I have simply written R. I mean, while I was describing the rectangular domain R, So then, in place of y, I think I had written r. Probably you have understood it, my mistake. Okay, please correct it. And again, in another juncture, what I did, I figured out that, I was talking about the very first approximation to the solution, y naught x equal to y naught. And then I was talking about the subsequent iterates, like say the very next iterate y1x. So then I somewhere, if you recall, I told this distance as y naught, but it is not this distance. It has to start from y equal to 0. Is it all right? Okay. Probably you have understood that also. So please, if from my last lectures recording. So please make these two corrections, okay, for yourself. Fine. So now let me again try to recall what we were doing. Hopefully you haven't forgotten that much during this weekend, during this holiday. So firstly, what we had, let us get back to the inputs that we have in our hand. So the very first input was the given differential equation. So y x naught equal to y naught. So this was number one. And then number two was the integral equation given by this. This is number two. Fine. Number three was the sequence, this defined by, let me tell you about simply the general term. Defined by this, and probably we call it A. Fine. And then again, I told you that this yn is nothing but the nth partial sum of the infinite series given by your y naught x plus I going from 1 to infinity yix minus yi minus 1x. So this I call B. Okay, and if you also recall, there were certain other conditions. There were certain other, not really conditions. I mean, from the continuity of your f and partial derivative of f with respect to y, we assume that this one was less than m, and del f del y xy less than k for all xy belonging to the rectangular region, original rectangular region R. Okay, fine. So these were the things, and then in the very last thing that I proved that all the this should write y and x, all the members of this sequence of functions, it belongs to the subrectangle R prime. Is it okay? Fine. So
yes.
And again, yeah, thank you. And again, we had also proved that your yn x minus yn minus 1x, this was less than equal to, I think, a kx. This, is it okay? I think that was it. Fine.
Yes, sir.
Yes, sir.
Yeah.
Yes.
Yeah. Okay. So now these were all the things that we had done in our last class. So now let us see what can we how we can proceed further. Okay. So we are going to take our journey from here. Okay. Assuming that we have already traversed all the stories, I mean, defined by 1 to A, B. I think I had written equation up to maybe 8 or something like that. Okay, fine. So now I told you that in order to prove that this sequence of functions is convergent, what I am going to prove that? What I am going to prove that the nth what I am going to prove that this infinite series given by B is convergent. Okay, fine. So now what I am going to do, you already know that this y and x I going from 1 to infinity, I going from 1 to infinity, yx minus y. This is less than equal to its absolute counterpart. Is it okay with everybody? Fine. Is it okay?
Yes,
Isn't it? We had already done this. We had
Yes,
already
sir.
done this. Okay. And then we have seen that this this term is your simply y naught. Okay. And then we have found out that your y and x minus y naught x, that was less than equal to a, right? Where we had defined a to be the maximum of all these modulus, right, for all x belonging to the subrectangle R prime. Is it okay? If you recall, this was so, right? Or simply, if you use this, the formula for the, general term, So then from here, what I will say that this series again it is less than a kh plus a kh squared, then your a kh to the power n minus 1 and so on. Okay, fine. And you see that this is nothing but, if I consider this infinite series, this is nothing but a geometric series with common ratio kh, which is less than equal to 1. Is it okay?
Yes, sir.
Fine. Okay. So basically, if I let n tends to infinity, this is going to give me simply a by 1 minus kh. Is it okay? Fine. It is going to give me that. And since kh is less than equal to 1, so what we can do, we can assume that, of course, kh exactly equal to 1, you cannot define this. Okay, fine. But I can simply say that, even without writing this, I can simply say that this is a convergent series. Okay, fine.
Yes, sir.
This is a
Yes, sir.
this is a convergent series. Fine. So eventually, the sequence is defined by a, it is going to be convergent. Okay, fine. It is going to be convergent, and of course, it is not only convergent; it is uniformly convergent, because for all x belonging to that closed interval given by mod x minus x naught less than equal to h, this is going to be true. Is it okay? Fine. So that means that means giving and sorry, firstly, okay, fine. Before that, let me tell you one thing. So now, see, this was a sequence of functions, right? So let us assume that this sequence of functions, it converges to a function y of x. Okay, fine. And now we have already proved that all the members of that sequence, it belongs to R prime. Okay. Is it okay? Fine.
Yes, sir.
And we have also from the expression A, we also know that all the members of that sequence is continuous, right? So this limit yx must be a continuous function in R prime. Fine? Okay. So in fact, as I have told you, this sequence converges uniformly to the function y of x. Okay? Fine. So, and since it is uniformly convergent, so we can say that given epsilon greater than 0, we can find a positive integer n naught such that your fn your y and x minus yx less than epsilon for all n greater than equal to n naught. Okay? And or we can simply write that if we make n sufficiently large, then the members of the sequence yn they are going to approach yx. And this I may write as limit n tends to infinity yn x this is equal to yx. Is it okay? Fine? Or I can simply or what I can say that yn minus yx tends to 0 as n tends to infinity. Fine? All of them are equivalent statements. Fine? So that means, you know, at the very beginning, when we set off to prove this theorem, we told you that we are going to do it in 3 steps. So how many steps have we covered till now?
2 steps.
Two?
One,
Any different?
we need to prove it is solution and the uniqueness.
Exactly. So step 2 was to prove that this is the solution, right? This is a solution, fine. And step 3 was that the solution is unique. Is it okay? Fine. So basically, we have just done only one step. It's pretty sad that after one day we have been able to do only more than one day, right? More than one class, we have been able to do only one step. But don't worry, step 2 and 3, they're not going to take that much time. Okay, I don't know how much time is it going to take, but our main concern is that we should understand all the concepts clearly. Okay, fine. I can, because now you remember what is 1, 2, A, B. Okay, fine. So now we are going to step 2. That means we are going to prove that yx is a solution of 2. Okay. So what was 2? That we have to prove that yx equal to y naught plus x naught x f t dt. Okay, fine. Or we have to simply prove that your, just give me a second. We have to prove that your we have to prove that this is equal to 0. Fine? We have to prove that this is equal to 0. Okay? So now let us concentrate back to the sequence given by A. Okay? Let us concentrate at the general term, that is the nth term in that sequence. Okay? Fine? So if you recall that nth term of that sequence, it was given by this. It was given by this. Okay. Now, so this means you please don't write anything. What I'm going to do, I'm simply going to change it. So this means this is 0. Fine. That's straightforward, isn't it? We already know that. These holes, we already know that. Say, let me call it maybe 9 or something like that. Let me call it 9. Is it okay with everybody?
Yes, sir.
I simply,
Yes, sir.
I have simply transposed the right hand side to the left hand side, and I have made the right hand side to be 0. As easy as that. Okay. So now, see, now our aim is to prove that this is equal to 0. This is equal to 0. Okay? So now this is equal to what? This is equal to this minus 0. Is it okay? I mean, if this expression is something like, say, capital X, so capital X is equal to capital X minus 0. Is it okay? Fine? What is
Yes,
that?
sir. Yes, sir.
Yes, sir.
Or X plus 0, whatever. So I am going to do X minus 0. Okay. So then what is going to happen? Instead of that 0, we are going to substitute the left hand side. Is it okay? Left hand side of 9. Fine. So this is going to give me, let me write it down so that so this minus this. Just a minute. This was y and x. No? This was y and x, not simply yn. Okay. So this is y and x minus y naught minus this f t y n minus 1t dt. Okay. Fine. So this is going to give me. This is going to give me your yx minus yn x, then this will be plus y naught will go. This will be plus. It's fine. It doesn't matter which way you are. X naught x and then f t fine. Okay, fine. Okay. So okay. So now let me concentrate on this. So basically, what we have got. That this expression is equal to this. Okay, fine. So see, so this is my left hand side, this is my right hand side. Is it okay? Although it doesn't appear that way, but we know that is the way we follow the sequence. Okay, fine. So now what I'm going to do, I'm going to take absolute value of both these things. Okay, so if I do that, then I am going to get yx minus y naught minus x naught to x f t y t dt. So this is going to be less than equal to your y and n. Fine. I can write it like that. No problem. Okay, and then plus x naught x, then the remaining. So f t y t dt. Okay. And again, in my last lecture, I think I have forgotten to finish this mod side in some of the expressions. Please bear with me for that. Okay, fine. So now let me concentrate. Let me concentrate on the second term on the right hand side of this inequality. Okay, fine. So now. Okay, so now obviously what I am going to do, I am going to concentrate on the mode of the term within the bracket, within the second bracket. Okay, the brace. Okay, so then from there, what you can get f t y n minus t this minus f y t, right? So now here you can see that your I have kept t fixed, right? My y coordinate is varying. Okay. So now if I apply Lingual Theorem, what this is going to give me, this is going to give me del f del y at some point t and right y star, okay, y star. And of course, I can write this as y star t, no problem with that, because that is again going to depend upon the value of t, which is fixed. Okay, where this value of y star t, it lies between the values of yt and yn minus 1t. Okay, and then of course I am going to have your yn minus 1t minus yt. Is it okay? Fine. So maybe I can simply write it like this. Okay, fine. And I know from the continuity of the derivative of f with respect to partial derivative of f with respect to y, I think this was less than k. Fine. Is it okay?
Yes, sir.
This was less than k, and of course this is going to be less than. This is going to be less than max of your yn minus x minus yx for all x belonging to R prime, isn't it? Fine.
Yes.
Fine. Okay.
Yes, sir.
So, yeah. So this is the thing. Okay. So I can write it a max your this yn minus 1x minus yx. Of course, you can write x belonging to R. Right? No problem with that. Okay. So that is why if I call it C, if I call it C. So from C, what I can write, that, or maybe I can continue here, or you can just, if you don't have space here, because I have space, if you don't have space, so you can simply write C implies or something like that. Okay, you adjust according to your own convenience. So from here, I can write this is your less than equal to yn minus yx, and then see here for this part I am going to get k into this. Okay, then I will be left with x naught to x integration dt, right? And from that part it is going to give me simply x minus x naught. Is it okay with everybody? Mod of x minus x naught, that was less than equal to 8. Fine. So that is why from here I am going to get k8 max yn minus 1x minus yx. Is it okay? Fine.
Yes, sir.
Fine. Okay. Now we have already proved that. The sequence y and x, this is uniformly convergent, to the function yx. Okay, so that means if we make n sufficiently large, this part is going to be 0 as well as this part. Is it okay? Fine.
Yes, sir.
If yn tends to yx, then yn minus 1x also will tend to yx, isn't it? Fine. So that proves that this is going to become what? If that tends to 0,
Yes.
Equal to 0.
this is equal to 0,
0.
right? That is going to be equal to 0, and from there I can have yx to be equal to y0 plus this part. Okay, so that means the limit of the sequence y of x, it is a solution to the integral equation 2. Fine. Second part done. Yeah, do you have any question? Okay. Fine. Okay. So remember, the next part is very, very important. I'm going to do a lot of geometric interpretation stuff once I do a couple of exercises. Okay, and then I'm going to ask you some questions. Okay, so the next part, please. I know that you guys are very sincere because you have been able to point out my mistakes. Whenever I do some silly mistake, you have been able to trace it out. Okay, so now I want you to have the same concentration here. The next part, what I'm going to do. Okay, fine. And that is going to give you also the answer to one very crucial thing that I told you, but nobody probably noticed it. Nobody probably noticed it that seriously at that time. I'm coming to that. See, we still haven't proved it completely, but we have already accomplished up to step 2. You know that we are going to accomplish step 3 as well. Okay. Now, if you recall, I have been telling about some wild assumption. Yes? Does it ring a bell? Can you recall it? What was the wild assumption? Remember, while we were trying to, choose H, we were doing something. Somebody asked me whether H is going to depend upon K or M. Then my answer was not very clear, probably. Like, I was telling that probably more on M than K. At least you remember that, right?
Yes, sir.
Yes, sir.
Right? Okay. So that assumption was this. Right? I had chosen my subrectangle R to be all xy belonging to that original rectangle R, such that your x minus x naught less than equal to h and y minus y naught less than equal to mh. I simply told you that this is going to work. So far it has been working, right? But why it is working? Slight hint you are going to find now. Okay, so my next step is step number 3. Step 3, we are going to prove that your solution 2 is unique. Solution 2 is unique. Okay, fine. Okay. So, sorry about this. If possible, let y tilde x also be a solution of 2. You know what is 2? You know what is 2? That integral equation. Solution of 2. And of course, then what must happen? y tilde x also must be a continuous function in R prime. Isn't it? It has to be that.
Yes, sir.
Yes.
Fine. But what is the guarantee that it is going to be that? See, eventually we are going to prove that y tilde x is equal to yx. There is no doubt about that. Okay. But the thing is that we firstly we have to guarantee that this y tilde x being a solution of 2, it also lies in that subrectangle R prime. Okay. So firstly, we are going to prove that the graph of y tilde x, it doesn't leave the rectangle R prime. Is it okay? Fine. You see, this is going to be very interesting and tricky. Please concentrate more. I'm going to spend some time on this geometry part. I want to be longer. Something like this. Okay. So this is going to be my okay, fine. See, this is x naught, y naught. This is of course x. This is y. Okay. This is y naught. This is x naught, and of course this is x naught minus 8. This is x naught plus 8. I shouldn't be bothered about these two, y naught plus mh and y naught minus mh. Okay, fine. See, what I'm trying to prove is that the graph of y tilde x, it doesn't leave this rectangle. It doesn't leave this rectangle. Okay, so if it leaves the rectangle, then what must happen? For some x belonging to this interval, I should get a situation like this. Are you getting my point? Isn't it?
Yes, sir.
Right? I should get a situation like this. Is it clear to everybody? See, if the entire graph for y tilde x for all the values lying in this interval, it stays inside the open rectangle R prime, then I would have a situation like something. Say, this is my ideal situation. I would have some situation like this, right? My y tilde x should have been something like this. Okay. So now we are going to assume that y tilde is not something like this, but it is something like this, and then we are going to prove that our assumption is wrong. We are going to get a contradiction. Is it okay? Have you understood what we are going to try now?
Yes. Yes.
Okay.
Yes, sir.
So then let me erase this. I'm going to ask you more questions. Okay, fine. You know that this is x naught y naught. Okay, fine. So now, if the curve is going to leave, the subrectangle R prime, suppose it leaves the subrectangle R prime for some value of x equal to x1. So here, x1. Okay, so that means at x1, the graph hits the rectangle at this point. Is it okay? Fine?
Yes, sir. Yes.
Yes? Okay. So now, say if this curve is y tilde x, so that means this length is going to be y tilde x1. Fine? Okay? Fine? So then this length is your y naught. Fine? So that means this length is going to be what?
Greater than MH.
MH.
MH, yes. This length is going to be MH. Greater than MH, I will come to that later on. Don't worry about it. Okay.
You are taking the point on this borderline.
Yes.
Okay.
Fine. So that means there exists a point x1 in the interval defined by x minus this such that your y tilde x1 this is equal to your y tilde x1 minus y naught, this is going to be equal to m. Is it okay?
Yes, sir.
Fine. It is going to be, because this is obvious. Sorry, MH. Okay, fine.
Yes. MH.
Is it okay with everybody? Please concentrate on the figure. It is going to be all right. Okay. And what is happening?
Yes,
Right? Okay. I don't know what is happening towards the right side, but I know that if my x lies in this interval, say this interval, so then what is going to happen? My this one, why not? This is going to be less than equal to mx for all your x lying in the interval this. I'll tell you. This x minus x1 minus okay. Just a minute. How to define that interval? For all x minus for all
Mod x minus
x,
x naught is equal to
x
x1
minus x naught less than equal to x1 minus x naught. Okay, fine. Is it okay? I should be fine. Yeah. Is it okay?
Yes, sir.
yes, sir.
Fine. Yeah. You just check. I'm talking about this interval. This interval is nothing but this one. See this one. It is centered around x naught. Okay. It is going to extend up to this length. Okay. If x minus x naught is less than equal to this length, then what is going to happen? I am going to get this. I think I should write strictly less than, then it will make sense. Yeah, yes, it will make sense. Yeah, because I want to eliminate exactly this point. Is it okay with everybody? Why I am making it strictly less than? Right? Because exactly at this point, I am assuming that this is equal to MH. Is it okay? Fine. Let this figure be intact. Someone is saying that it is greater than strictly greater than MH. Somebody uttered that word. I'll come back to that. Okay. So you have understood this. Okay. Fine. So now. And again, this figure is there in Simon's book also. You can follow from there. But see, again, if you don't understand it right now, you give one or two more reading and go through again Simon's book. It should be clear to you. So Therefore, your see this is simply y dot is simply y x naught, isn't it? Fine. So that is why I am writing the corresponding argument here. This. Okay, fine. And see, this was what? This one was equal to mx. What about the denominator? Okay, let me write it down once again. This. Okay, so now you can see that because x1 lies in this interval, in the entire interval. See, x1 is a point in the entire interval, right? So that is why this distance x1 minus x0, it is always, the mod of that is always going to be less than
H.
Or from here, or less than equal to h. No problem about that.
Sir,
See,
sir, I have a question.
here, sorry, just a minute. From here, see, here, what is going to happen? Your x0 minus, sorry, x1 minus x0, x1 minus x0, it is always going to be, because this is an interior point I am taking. x1 is an interior point, right? Just a minute. Let me come to this interval again. See, I am considering. Okay, fine. And I am assuming that x1 is an interior point. It cannot be the end points, right? Okay. It is x1 is not the end points. X1 is not also equal to x0 also. Okay, fine. So then what must happen? If x1 belongs to this interval, which is an interior point, then this one, your x1 minus x0, it must be strictly less than h, isn't it?
Yes, sir.
Yes.
Isn't it? You simply think about it. Say, suppose this is x0, this is x0 minus h, this is x0 plus h, right? And I am taking a point here in this interval, which is not the endpoints as well as the center point. Okay, so then if this is h, this distance is h, suppose your x1 is here, right? So then mod of x1 minus x0, it must be strictly less than h. Fine. Okay, so
Yes.
that is why. So if this is strictly less than 8, so 1 by x1 minus x0, this is going to be strictly greater than 1 by 8. Okay, so that is why from here I am going to get it mx by 8. This is equal to m. Okay, fine. Okay, now
Sir,
yes.
sir, x1 is the point where the graph cross the rectangle at that
Exactly.
point. That's pre-image.
Yeah.
Pre-image.
Yeah.
But if the graph meets the rectangle at the corner point, then it can happen that x1 is the end point.
No, I am assuming that, yeah, you have a point. You have a point. Now, okay, fine. So I'm not assuming that, because that is, in fact, it is not going to violate. That is not going to violate y mod of y minus y naught less than equal to mh. You got my point?
Yes,
All
sir.
the way. Only when this yx, something like y tilde x, only when it violates, some relation like, only when it violates this, right?
Yes,
Then
sir.
only,
Yes, sir.
right? So it is not going to violate. So that is why, and that is why what people do, you will see in most many books, to be on the safe side, they simply consider an open rectangle or open interval. Okay, so that they can eliminate those points as well.
Oh,
Fine?
okay, sir.
Yeah,
Okay.
fine.
Sir,
Yeah.
sir, I have a question.
Yes.
Sir, in the downward, you took a inequality that this mod x minus x naught, this less than x1 minus x naught, modulo of this. So my question is, in the you did everything in the right hand side of this, but if the
Yes.
side may be
Thank you very
smaller,
much for that.
then this will
Yes.
not hold.
Yes. I understand that. Yes. See, even had you taken it here, say, suppose had I taken it here somewhere, had I taken it somewhere here, still it would have worked. Say, let this not be, I mean, that symmetry. Let it be something like this. Okay. Even if your x1 was here, thank you for this question. I was expecting that. So this is, even then it is going to hold. You simply check. Because I am using mod, you remember. I am using mod. Fine?
Yes.
I am using mod. In that case, see, this should have been, just a minute. In that case, this should have been y, and this should have been y tilde x1. So the same thing would happen because I have taken the mod, isn't it?
So we have to take the minimum of those two lengths.
No.
Minimum.
Why? No. I'm taking the mod now. So because your this distance and this distance both are mh and mh.
Yes.
Isn't it? Earlier you got this as mh. Now what you are going to get? You are going to get this as mh.
For this picture, it is right. This inequality is right. But if my LHS is smaller than the right hand side, means the curve is smaller.
Even then, I am
then,
going to take x1 to be an interior point. It is still going to be varied.
Yes, sir.
It is going to be varied. Don't worry about it. You check because we are on the safe side because I am using mod. Okay, and m is a I mean it's a positive integer. M is a positive integer. Sorry, not necessarily because here we were simply talking about a bound. So m is a positive number, positive real number. Okay, fine. I'm going to actually tell you what m will turn out to be. So if we assume that the graph of the function y tilde x is leaving this subrectangle R prime, we have seen that we are getting this inequality. Okay, but now what is happening? I mean, y tilde x, it is a continuous function. It is a continuous function. This is x1, this is x1 minus x naught. Okay, so if I use Lagrange's mean value theorem, now say this is simply equal to your y tilde x minus y x naught. Okay, and it is x1 minus x naught. Okay, so then just a minute. I can write it as also y tilde x naught because it has come from the same initial problem, right? The function must satisfy the same initial condition also, right? Okay, so then from here, if I use mean value theorem, what I'm going to get?
y
This is
tilde
equal
from
to
lambda
some derivative, yes, some derivative of the function at the point
Y
x star, right? Where x star lies between x0 and x1. Okay, and since just a minute, let me tell you one thing. See, originally I was considering this as a function of both x and y. Is it okay? Fine, right? So here, just a minute. This is sorry. This is y prime x now. Okay, fine. Isn't it? Because the function is y.
y tilde prime x star.
Y tilde prime.
Yes, sir.
Okay, fine. So then, and what is your y tilde prime x naught? Again, from the given differential equation, this is simply your f prime x naught and something like y tilde x naught. Isn't it? Fine.
There is no f prime.
Prime.
It is
Y
just simply f x star y tilde x star.
Sorry. Yeah. Thank you. Okay.
Yes, sir.
Yes. So now see. Now you give me one thing. Obviously, this x star. Obviously, this x star is some point between x0 and x1, right? Okay, and y tilde of x star. So this point x star, y tilde x star, right? This point is going to lie in R prime. Is it okay? Fine. So making use of the continuity of the function, f in R prime, what must happen? This must be less than equal to m. Sorry, not m. Isn't it? This is what we assumed at the very beginning by the continuity, which implied the boundedness of the function in a like say closed domain. We got this, isn't it?
Yes, sir.
Fine.
Yes,
So
sir.
we get a contradiction. So that means this y tilde x, it must lie inside the subrectangular domain R prime. Fine. So now we can prove the uniqueness. So for that, what we are going to do, like so now we have since your both yx and y tilde x are solutions of 2, that integral relation 2. From there, we are going to prove the uniqueness, and that is pretty straightforward. Okay. So, and please, I mean, at home, you please try to draw this again. You try to interpret it on your own. It will be clear to you. Okay. So maybe, I mean, I'm running out of space here, so you make it bigger. Okay. So then it will be clear to you. The board is looking very dark. Okay. Okay. So now your y tilde x minus yx. So this is what. Let me write it down. dt minus fine. So what I'm going to get your yx. So this is x naught to x, your f of t y to the t minus f of t y t dt. And you know, as before, from here, what we would have got? We would have used what? Lingual Theorem, right? For the, using the partial derivative with respect to y. Isn't it? Fine. So,
Yes, sir.
just simply think about it. Right here, see, it is the what is varying, y is varying, isn't it? Right. So del f del y t something like y star. Okay, then your y tilde t minus yt, isn't it? I have got something like this. Fine, from that part. Okay, so then for this is less than equal to k. Fine, and again this is less than max y tilde x minus yx for all x in R prime. Is it okay?
Yes, sir.
Yes.
Fine. So that is why this is less than equal to, this is less than equal to k, and then max y tilde x minus yx for all x belonging to R prime, and of course from this part x naught to x integration dt, I am going to get mod x minus x naught, right? That is less than equal to 8. So that is why k is into this. Is it okay? Fine. So I have got this basically. I have got this. Okay. Fine. So now that means if you take max of all of this, if you take max of all of the left hand side, that would have given you your max of y tilde x minus yx less than equal to kh, max of y tilde x minus yx for all x belonging to. Fine. Okay.
Yes, sir.
So what conclusion? Yes. Can somebody tell me what conclusion we can draw out of this?
KH is greater than 1, greater than equal.
So that maximum of mod y tilde minus y should be 0.
Exactly.
Otherwise, k
Yes.
is
Otherwise, we get an inequality, which is impossible because we have already assumed that KH is less than equal.
less than 1.
Just a minute. Here. I think we had assumed strictly. We had assumed KH strictly less than 1. Remember, not when the sign was not there. Is it okay with everybody? So please look at this inequality, right? See, if the term inside the modulus it is not 0, so then what happened? Because it is non-zero, I can divide it by that term, max of this. So that is going to leave me. With this KH is greater than equal to 1, which is impossible, isn't it? Which is impossible because I had chosen my H in such a way that KH is strictly less than 1. Only then we are going to get that uniform conversion. Because see, if you recall that some of the conversion series was something like A1 minus KH. Okay. had kh been equal to 1, it would have been undefined, isn't it? Only in case kh strictly less than 1, we get a geometric series which is going to be convergent, and the limit of that sequence was this. Is it okay? So now I think we have accomplished this feat, like proving the uniqueness and existence theorem. Is it okay with everybody? Yes.
Yes, sir.
Yes, sir.
Please practice it at home. Again, as I have been reiterating that although I am explaining a lot of stuff, I'm not writing down systematically because it is going to take a lot of time. And you already have Simon's book, which I have provided to you, right? And what you do, I mean, like say maybe in the evening or something like that, when you have finished up all your classes, so then sit down and go through it once again and write it down, I mean, immediately. Otherwise, if you again, I mean, wait for some time to do the things that I have told you to do, then the memory, I mean, it is not going to be fresh. Okay, so please write it down systematically according to your own convenience, using your own language, and I mean, the proof will be much more easier for you. Okay, fine. So now, can somebody tell me, after we have done the third part, why that wild guess worked? Why that wild guess worked? And I am again going to come back to the corner point. Somebody was telling me about the corner point. Somebody was telling me about greater than m also. Okay, let me come to that. Yeah, so meanwhile, you please think why that wild guess was working while proving this theorem. I'm going to pose it in a different way. Just give me a sec. You just for the time being, you just think about it. Okay, have you figured out why it works? Mod of y minus y naught less than equal to mh.
Sir, what is the question, please?
My question is that, see, at the very beginning, I told you that the way we have chosen h, and for that matter, the way we have chosen the subrectangle r prime, right? So here I have chosen this interval, right? And the y range was chosen to be y minus this, okay? And based on this fact, I have put that this y tilde x, or for that matter, in fact, not only y tilde x, any solution of the equation is not going to leave the rectangle r prime. Okay, so now see, I didn't give you any reasoning behind that, why I had chosen it that way. Eventually it worked, right? But I didn't tell you why that works. Isn't it? Fine?
Yes, sir.
I didn't give you any explanation. So let me come back to that. Oh my God, the board is a mess. Okay, so now let me come back to the concept of integral curves. Okay, if you recall, like integral curves were nothing but solution curves. Okay, integral curves were nothing but solution curves. Basically, they were nothing but the graphs of particular solution. Okay, and graphs of those particular solution, you are going to get it through, plugging in some values to the parameter. Okay, fine. So now, suppose I am seeking a solution in the neighborhood of this point x0, y0, right? In that rectangle R. Always remember, I am seeking a solution in the neighborhood of x0, y0. So that is why I'm not worried about a very big interval. Okay, it may not be so that the differential equation is differential equation does have a unique solution in the whole real life. It is not like that. Okay, I need some solution in the neighborhood of this one. Okay, fine. And as I have told you, the equation is given by this, your yx not equal to y naught. Fine. Even if I don't solve it, what you know that this f of x y is going to give you the slope of the tangent to the solution curve at a particular point, right? So then, say suppose this was your rectangle, okay? And suppose I am choosing this rectangle in such a way that x0, y0 is at the center of that rectangle. Is it okay? So basically, what I can do, I can choose my rectangle. To be a set of points in R2 in such a way that your x minus x0 is less than equal to a and y minus y0 is less than equal to b, where a, b are strictly greater than 0. Is it okay? Fine. So how I can choose it? I can choose it to be something like this. So if this is x, this is y. So what is going to happen? So now this is x0 minus a. This is x0 plus a. So similarly, y0 minus b. This is y0. This is x0. This is y0 plus b. Okay. So now let me start with this point x0, y0. As I have told you, this is going to give me the slope of the tangent to the curve at that point, x0, y0. So if I find out your f at x0, y0, I know the slope of the tangent. Say, suppose the slope of the tangent is positive. So then what we have to do, for positive values of x, you go higher up. So for 1 unit of x, you go, like if this is equal to say m, you go m unit up. Okay, if the slope is say negative, then I go 1 unit right and m unit down. Is it okay? Fine. Say suppose in the neighborhood it is for the time, let us assume that is positive. So then, like from this point, I can draw a vector like this. Fine. Okay. So then it leads me to another point x0, y0. Fine. Over there again, I try to find out the slope, and in that way, it is going to lead me to the shape of the graph, kind of, right? And similarly, say suppose I'm still assuming that the slope of the tangent here at this point is positive. So what about see, so far I have considered only points towards the right of x0. So what about the points towards the left of x0? So for that, like say, I will be moving -1 unit towards left and again 1 unit down. Sorry, m unit down if your m is the slope. Is it okay? Fine. So here I can get something like this. So basically what I want to tell you that, so even without solving it, there is a possibility that you have the idea of the shape of the graph, of the solution curve. Is it okay? In the neighborhood of x0, y0. Is it okay?
Yes, sir.
Yes, sir.
This concept is fine. So similarly, had the slope been negative here in the neighborhood, I will have something like this. I would have something like this. I would have something like this. right? Basically, what these two curves are, I mean, in fact, they are not actually curved. We can say that these are nothing but some piecewise approximating polynomial, isn't it? Because they are different. I mean, they have been drawn in certain small intervals, isn't it? The first interval is like say maybe x naught plus epsilon. The second interval is x naught epsilon to x naught plus 2 epsilon and so on. Is it okay with everybody? Right? So now, one thing you see, what is f of xy? F of xy is nothing but the slope of the, I mean, tangent to the curve. Okay. So now, what is going to happen? What is going to happen? If you know the bound of this, I know that any slope of the tangent, it cannot go higher than minus m or lower than, sorry, higher than m and lower than minus m. Is it okay with everybody?
Yes, sir.
Right? So I am,
Yes, sir.
and remember, I am talking only about the neighborhood of the point x naught, y naught. So now, if I want to draw a straight line passing through x naught, y naught, and having slope m, then say, suppose this is my curve, this is my straight line. Okay, so this is y minus y naught equal to m into x minus x naught. Fine. So similarly, I can draw y minus y naught is minus m x into x naught also. So it is simply going to be something like this. It is simply going to be something like this. Okay. Is it okay with everybody? Fine. Then you will see that under this condition, in the neighborhood of this point, if I draw this approximating polynomial, right, they can never go beyond this line up. Why? Can this situation happen? The last one. Can this situation happen? Can the approximating polynomial vectors, can it be something like that? You got my point or not? You think about, if this happens, then what is going to happen?
Sir, if this happens, then function will not be bounded by m.
Exactly, right? The function is not going to be bounded by m. The slope is, the curve is, if the curve is like that, that means this statement is going to be wrong. Is it okay? Fine. Is it okay?
Yes,
That
sir.
is why, like say, if you draw, I mean, two straight lines like this, if you draw two straight lines like this, then I can always guarantee that all the solution curves are going to lie in this set of portion. Is it clear to you? So now you think at home why it works. Okay, in my next class again I'm going to come back to this, and then I'm going to tell you the alternate statements. Alternate statements, like statement is the same for existence and union. Only the way they define the subrectangle R prime, it is different. So I'm going to tell you is that based on this concept, how in other books they define the subrectangle. Okay, fine. So I think I'm going to end my class today. It has taken more than 1 hour 15 minutes. Sorry for that.